And I need to open the different. Okay. So you're doing your seating chart. Yep. I've got iClicker loaded. I need not that. Flashback. All right, so we are 1:30. Everybody got their exams, they're alphabetical, so you should have been able to find them pretty easily. Just make sure that you turn them back into that black basket over there before you leave. So you can get up and turn them in anytime as we're chit-chatting, doesn't bother me. No big deal. Any questions on the exam? It is cumulative. So like if you miss some and you want help, I'm happy to help you. You know, just make an appointment and let me help you. Come to my office, we'll Zoom, whatever it is, we'll find some way to do it. And I'll help you because the exam, the final exam is cumulative. So you can't just forget about this material and figure, well, I survived, right? So if you need help, please ask for it, okay? Any other questions about the exam, anything? Okay, and y'all got the notification that I reopened chapter 5? So I don't know what happened with y'all, but my power went out when the storm hit. As soon as the storm hit, my power went out. I was out until like 5 o'clock this morning. So, yeah, you know, I don't know if that's happened to other people. So I just extended it. Yes, ma'am. Did it save your progress? Maybe clear your, so whenever I have problems like that, what I do is I clear my cookies, my browsing history. It's like, I don't know, it gets like clogged. I don't know. It's probably not the right word for it. But if you go into settings on your browser and then search like clear cookies, and that's one of the things. And usually that'll fix it. Usually. Yeah. Anybody else? Good. Okay. So we're going to pick up on chapter 6. So get your iClickers out. We're going to do some iClickers. Hopefully. There we go. All right. Y'all ready? It's okay. All right. So remember, you have 1 minute to answer, and then you can phone a friend. So select the correct match between the term and the description. The correct match between the term and the description. Remember, you have 1 minute. Okay, you got about 5 seconds left. Make sure you ring in. Okay, turn and talk to your friends and then click in again, 30 seconds. And on Zoom on chat, you can chat too. You are participating online. And don't forget to do the seating chart. Did I tell you how to do the seating chart? Some days I forget. Okay, so 5 seconds. Make sure you ding in again. What do we have? 40 something? 41, 42? I thought maybe. Okay. So what did y'all say was the correct answer? Oh, awesome. B. Okay, so we did go up. We even went up all the way to 100%. That's awesome. So it is a disaccharide. I'm using the wrong pen. It is a disaccharide that reacts with water to produce 2 monosaccharides. Okay, let's try another one. Remember this. What is the highlighted functional group? Just the highlighted portion. What is the highlighted functional group? Okay, 10 seconds. Maybe we didn't have 40. Maybe it was the beginning. Oh no, we did. Okay. Turn and talk to the people around you. Click in again. So make sure you click in again before 30 seconds is up. Okay, click in again. Come on, y'all. 30 seconds. Click in again. We had like 41. Next time I'm going to cut it off at 30 seconds. We had 41, I think. I think we had 41. Okay, so what did we say? What is the highlighted functional group? The highlighted functional group is a ketone. It is a ketone. So we went up quite a bit. No, it's an aldehyde. What did I say? It's A, it's an aldehyde. And I'm just looking under A as a ketone. It is not a ketone. It is an aldehyde. If I could see, it's too much on one screen. So if it's an aldehyde, what's our little thing to remember? It's all what? Alone aldehyde, right? What was the other one that was picked? It's either B or E that was picked. Yeah. So why is it not a carboxylic acid? But to be a carboxylic acid, you have to have an OH. You have to have a hydrogen that can disassociate. So this would have to be an O there, right? But there's no oxygen there. And why is it not a ketone? Because you need 2 R groups instead of having 1 R group. Yeah. Okay, y'all ready? Okay, what is the highlighted functional group again? Sometimes I'm nice. Sometimes. Most of the time, I like to think. Or I'm going to close it at 1 minute. So 10 seconds. All right. Talk to your neighbors. I don't think you really need it on this one, but talk to your neighbors. 30 seconds. Oh, that was quick. I must know y'all answered. Remember, 30 seconds, ring in again. Don't forget to do that second time. Okay, so what did we say this time? Good, we did say it is B, it is a ketone. Let's go back the other way. Okay, so how do we know it's a ketone? We have two R groups. So here's an R group and here's an R group, right? So that's what makes it a ketone. I want to point out one other thing while we have this up on the screen. You know, it's a little bit weird how they drew this molecule, right? So really, if we're drawing a sugar, right, we have that carbonyl carbon, right? And if we have an R group above it, how do we write that? We write carbon, and there are two hydrogens, so we write CH2OH, right? And then what happens? Then we come down and we show our anomeric carbons. That's an anomeric, that's an anomeric, and then the last one, ooh, is not anomeric, right? So that's a C what? H2OH, and then I just fill in my anomerics. Right? Does that look a little more like what you're used to? Right? It's the same thing. So whenever you see that CH2OH, what are you actually looking at? That is the same thing as CH2OH. And it's the same thing down here as it is there. Okay. Yeah. All right. I think one more. Oh no, I didn't do this one. I didn't do this one with the other class. But we'll talk about it. I'm not doing this as an eye clicker because I'm making sure y'all each have the same amount of points. But what's the highlighted functional group? Say it out loud. It's an alcohol, right? So if we find our OH and we go to the carbon next to it and we look at how many R groups are attached to it, how many do we have? 1, 2, so it is a secondary alcohol. But I didn't do that one with the other class, so I'm not doing it with y'all. Got to stay on the same number of points. Okay, now we switch over to our in-class problems. I'm going to try something new. Screen. I'm joining the Zoom with my iPad. So that hopefully I can do this. Yay! All right. Okay. So remember how we were working on our set of definitions? Remember this? So we did an enantiomer, right? We said that was a mirror image. We did isomer. Yeah, okay. So an isomer can either be D or L, right? And how do we know if it's D or L? We go find the farthest chiral carbon. We look at the hydroxyl. Is it on the left? If it's on the left, it is L. If it is on the right, it is D. Okay, so we got that. Those are the only two we did? We did epimer? Yeah, we did epimer. So epimer is if you have that straight chain and we're looking at one of the carbons and only one of the carbons do we have the hydroxyl and the hydrogen flip-flopped, right? Okay, there is one more possibility. There's one more possibility, and that is called a diastereomer. A diastereomer means it's not an epimer and it's not a complete mirror image. So this is in between the two. It's not one, it's not all of them. It's more than one, but not all of the chiral carbons. The H and the OH are swapped or flip-flopped, however you want to say that. So might you put these on flashcards to practice the terms? That would probably be a really good idea. So you're just adding that to your list of definitions. I'm hoping my battery life makes it an hour and a half. So I'm reducing my screen. All right, so now we have to come and look at some molecules, and we have to identify them as being either an enantiomer or a diastereomer. So remember, enantiomer is our mirror image, and our diastereomer is, we'll say more than one. That's flip-flopped, right? Okay, so number your carbons. So always the first thing that I do, if I'm looking at this, how do I know where to start numbering carbons? I find my carbonyl carbon. So carbon in the double bond is 1. If there was a carbon that was above this, would the carbonyl carbon be number 1? No, the carbon above it would be number 1. That's really important. Don't forget that. 2, 3, 4, 5, 6. Do you notice in A, B, and C, how many carbons does each have? Same number, right? So what's different between D-glucose and the structure in A? If you have anything different and it's not chiral, it doesn't matter. So all we're really looking at are those chiral carbons. So what's my first chiral carbon? Carbon number 2. So is carbon number 2, are the hydrogens and the hydroxyls in the same orientation or different? They're the same. Okay, how about carbon number 3? Same or different? They're different. So what I like to do to kind of keep track is just to highlight them. And then I don't have to keep going back. Carbon number 4, same or different? Different. Carbon number 5, same or different? Same. Okay, is this a mirror image? No. Is it an epimer? No, it wasn't even a choice, really. An epimer would have been if only one were changed. I have 2, so what do we call this? A diastereomer. S-T-E-R-E-O-M-E-R. Oh my goodness, I really can't spell. Diastereomer. Were you ever going to have to actually spell it on the exam? You will not. Isn't that magical? Okay, look at B. Look at B. Let's do the same thing. We're going to start with carbon number 2 because it's the first chiral carbon. Same or different? Different. Carbon number 3, same or different? Different. Carbon number 4, same or different? Different. Carbon number 5, same or different? Different. What is this one? This is an enantiomer. To go to the side, enantiomer. No, I'm going to have to squeeze C in too. All right. Oh, I forgot to tell y'all a joke today. That's a really good one. All right. So why was it really important for the meteor shower that killed all the dinosaurs? Why was it really important for the Earth? It was for the crater good. It's for the crater good. All right. Okay, C. Carbon number 2, same or different? It is different. Carbon number 3, same or different? Different. Carbon number 4, same or different? Same. Carbon number 5, same or different? Different. What is this one? Diastereomer. Not too bad, right? So long as, but like when you get to the exam, if you start seeing all these crazy new words and you don't know what they mean, you're going to struggle, right? So get really comfortable with the vocabulary and then start applying the vocabulary. Okay, so I'm a huge proponent of like flashcards for vocabulary, you know? And here's a trick. Has anybody ever told you this? You know, when you're doing those flashcards, if you do like them on the computer, you do the, what do they call that? Quizlet. If you want to really know if you've got it or not, and you're doing the cards, have a sheet of paper next to you and a pen. Put the definition, write down the word before you flip the card. Because if you don't, you're going to assume you know it and you might not, or say it out loud. I always like writing it. I think it helps me remember, but either say it out loud or write it. Otherwise, you're going to think you know it and you might not. Okay, it's a good study tip. Okay. All right. So use the structure of D-glucose to answer the following. So I gave you D-glucose. Draw the Fisher projection of the carbon-3 epimer. Then draw the Fisher projection of L-glucose. So when I do A, I'm only going to mess with which carbon? Carbon-3. When I draw B, what am I going to draw? A mirror image, right? I go from D to L. All I'm doing is a mirror image. Okay, so let's see if I can do this. Oh, okay. So this is what I had, right? What do I need to change in order to get to what I want? Do this. What am I going to change? Carbon number what? Carbon number 3. So let's make sure that I name it right. Here's carbon 1, 2, 3, 4, 5, 6, just because I love numbering carbons. It's my favorite thing to do. So I'm going to go to carbon 3, and I'm going to get rid of what's attached to carbon 3, right? And I'm just going to add in my reverse. So what should be on the left? Hydrogen. What should be on the right? OH. So we call this one the carbon 3 epimer of D-glucose. See how that's the only thing that I did differently? Everything else is exactly the same. Okay, so now I want to do the mirror image. So I'm going to take that same thing and I'm just going to remove everything that's on the left and everything that's on the right. Whoa. So I remove everything on the left, everything on the right. Oop, not that one. Because we're not going to mess with anything that's not chiral, because it really doesn't matter if it's not chiral, right? So then everything that was here, whoa, everything that was here on the left will be what? On the right. So I'm going to go and do that. So I'm going to put it on the right. I'm going to go H, OH, H, H, and then I'm going to come over here. I'm going to say everything that was on the left is going to go, everything that was on the right is going to go on the left, right? So I'm going to put OH, I'm going to put H, OH, OH. So what should we call this one? I should call this one L-glucose. Now, you know, what form are almost all the sugars that are in the natural world? D or L? They're D. Sugars are Ds. Because our enzymes are in the three-dimensional conformation that can metabolize D sugars. We can't metabolize L sugars. If all you ate was L sugars, you would starve and die. Now, you could also make some money. If you could make L-glucose in high quantities for a cheap price, why would you be a millionaire? Yeah, right? We can't taste the difference between D and L-glucose. It would taste exactly the same, but our cells would not be able to metabolize it. So you would have the perfect diet sugar because you could taste it, taste exactly the same, but you would not be able to metabolize. Wouldn't that be cool? All right. As I digress sometimes, right? Okay, identify the monosaccharide that fits each of the following descriptions. So this, in this case, for this portion, you do just have to know these. Like you just have to learn these, get yourself some flashcards. And in the later sections, they'll ask you things about disaccharides. So flashcards. Some of these you might know already, but flashcards. Okay. So in combination with glucose produces the disaccharide lactose. What do we have? Any guesses? Not glucagon, but galactose. The G-L-A-C-A-T-O-S-E, galactose. So where do we find lactose? Milk, right? People are lactose intolerant. So they're intolerant of the disaccharide that is glucose and galactose, right? Okay, also called blood sugar. This is glucose. So D-glucose. D-glucose. Okay, also called levulose. Anybody heard of that before? You heard levulose? No? Excuse me. So that's D-mannose. I think you have 1, 2, 3, 4, 5, 6 monosaccharides to learn. It's not very many. It's really not very many. So don't freak out too much. So, you know, in the past, we've talked about how your body regulates blood sugar levels, right? You eat a meal. What happens to the amount of sugar in your bloodstream? Goes up, right? Okay, so that sugar in your bloodstream, your cells need it to survive. But if you pull that sugar out of the bloodstream too quickly or too much, your blood sugar is going to tank, you're going to pass out, and you're going to go into a coma, right? So you have to very tightly regulate that in the body. So when you've eaten, your body's going to produce a hormone called insulin, right? So when the cells get this hormone insulin, it tells them, hey, you can pick up the blood sugar, the sugar that's in the bloodstream, and you can use it to make ATP, right? And the opposite is true. If your blood sugar gets too low, your body releases glucagon, and glucagon actually tells parts of your body, hey, our blood sugar is really, really low. You actually need to put some into the bloodstream, because the brain uses glucose as its primary energy source. So if you don't have enough glucose in your bloodstream, your brain's not going to work, which is really, really dangerous. Anyway, so there are 2 forms of diabetes. If you don't have enough insulin, your body just does not produce enough insulin, you can have diabetes, right? It's an inability to regulate your blood sugar. Or you can produce the insulin, but your body doesn't respond to it. So a lot of times, if you don't make insulin, you've never made insulin. And so you're going to diagnose that very, very early on in a patient's life, right? So we call that type 1. So most cases begin in youth. Those are type 1. So in type 1, remind me, what's the problem? You don't make enough insulin. So insulin production is low. So then B, insulin is often present, but glucose is not transported into cells. That's type 2. And type 2 is typically diagnosed later on in life. But the good thing about type 2 is that you can actually train your cells to be more responsive to insulin just by controlling your diet and exercise. So C should be type 2. Okay. All right. So the next thing we need to talk about are sugars. If you go on, let's see, it's looking at sugars. How is this sugar different than the sugars that we've been looking at so far? Does this look like a Fisher diagram to you? Does not look like a Fisher diagram to me. Okay, so get out a sheet of paper. I'm going to show you something or your notes or whatever it is, but get something else out. I went over this in lecture if you watch the lecture, but I feel like this is something that is kind of good to see twice. So we start out with sugars in the Fisher diagram, right? So I'm going to go ahead and I'm going to draw the Fisher diagram for a sugar. We're going to give it 4, 3, 4, and we're going to give it CH2OH. And we'll give it OH and H, OH and H, OH and H, OH and H. Okay, so this is a typical Fisher diagram. Now, up until now, we've been lying to you. Sugars don't always exist like this. Most of the time, sugars are going to exist in the ring form. If something exists, it's in a straight line, how am I going to convert it to a ring? Fold it back in on itself, right, and attach the two ends. But the question is, what bonds are being formed and what bonds are being broken to go from a straight chain to a cyclic form? That's what they call it, the circle form, right? Okay, and it all has to do with polarity. Now remember polarity? Yeah, a little bit. Things that are different electronegativity values hog electrons more. The more they hog electrons, one atom becomes partially negative, the other atom becomes partially positive. Remember that? Okay, so I want you to focus on two particular oxygens. We're going to focus on the oxygen that's in the carbonyl bond, right? And then we're going to focus on the oxygen that is on the chiral carbon farthest from the carbonyl carbon. You with me so far? Okay. Now, if we kind of zoom in on these in particular, right? And I say, okay, here's my carbon, double bond, I have a hydrogen here, and I'm just going to call this rest of the molecule, right? This is what is going to interact, and let me put my green oxygen. It's really important that we distinguish them. This is going to interact with this. That's why I've highlighted the two. This is where the ring is going to form. So how and why does that ring form? Well, remember we talked about polarity. So if I have a carbon double bonded to an oxygen, which one is more electronegative, oxygen or carbon? Who's closer to fluorine the floozy? Remember that floozy? She wants everybody's electrons. Oxygen is more electronegative. So oxygen is going to hog those electrons and oxygen is going to become partially negative. Remember how we drew that? Right? So what atom becomes partially positive? Carbon becomes partially positive. Okay, now I'm going to take the bottom part of that molecule and I'm going to bring it up to the top. So I'm only going to show you a piece of it. Okay, so I'm going to show you the oxygen. So here's the oxygen. This oxygen right there is going to be this oxygen right here. And it's attached to a hydroxyl. It is a hydroxyl, so it's attached to a hydrogen. And we have the rest of the molecule, right? If I have oxygen in a bond with hydrogen, is one of them going to hog those electrons? Who's closer to fluorine the floozy, oxygen or hydrogen? Oxygen. So oxygen is going to become partially what? And hydrogen is going to become partially what? What do you notice? I've got some partially positive things close to some partially negative things, right? And opposites attract. So I'm actually going to, lo and behold, make a new bond between the negative and the positive. So this is a new bond. So that's really awesome, but I got a problem. Tell me my problem with carbon now. 5 bonds. That's not going to happen. So what happens when we add something new to something that has a double bond? We get rid of the double bond. So I'm going to get rid of one of these, right? Now, how about my oxygen? Is my oxygen up there happy? Absolutely not. Absolutely not. He needs another bond. Who's he going to bond with? Oh, look at this, a partially positive hydrogen. But this hydrogen can't make two bonds, so what's going to happen? I'm going to lose that bond, right? So I've lost two bonds and I've gained two bonds. What does that mean in terms of our Fisher diagram over here? Where are those new bonds occurring? The new bonds, the first new bond that I showed you between the carbon and the oxygen is between the carbon and the oxygen. Now that looks really far away, doesn't it? But if you took the two ends and folded them, do you see how it would be close? Right? And we showed all those stick molecules, and we showed that we can rotate them about the different bonds, so they can fold in all kind of different crazy conformations. So it's not unheard of. It happens all the time. Okay, so that's one bond that's going to happen. And then the other thing that's going to happen is I'm going to take this hydrogen away from here, and I'm going to put it up here. Right? Okay, now, this is a crappy way to draw a molecule, right? It just doesn't make sense. But remind me how we number our carbons. Start with the carbon closest to the carbonyl carbon. And if there's nothing close to it, start with the carbonyl carbon. So that's 1, 2, 3, 4, 5, 6, right? Okay, now, how many atoms are going to participate in the ring? I have 5 carbons, and what else? So I have carbon 1 right here, go down carbon 2, down carbon 3, carbon 4, carbon 5, and what? An oxygen. It'll pick up the oxygen. The oxygen is in the ring. So how many members do I have in my new ring? 6. 5 carbons, 1 oxygen. So when you draw it, draw your oxygen first. It's my green oxygen. Then I'm going to go and I'm going to make a ring. So a 6-membered ring looks just like that. Well, sort of, not the best artist. Okay, that's my ring. Where is carbon 1 in the ring? It's right here. You always go that way. Always go that way. And you're always going to get it right. Now go in a circle and finish numbering. 2, 3, 4, 5. Those are my carbons. How many carbons were originally in my sugar? Where's my 6th carbon? It has to be attached to carbon 5. I have to go up. I have to extend. I got to go out of the ring. Either it can go down, indicating that it's below the ring, or it can go up, indicating that it's above the ring. If I took a ring and I put something up, right? If I flip it, then it's down. So it doesn't really matter, but by convention, we always put it up. So, right, that's up. This would be down. So I always put it up. And so I'm going to put CH2OH. Okay, you with me so far? Now, I don't want to deal with carbon 1 yet. I want to deal with the rest of the carbons, and then we'll come back to carbon 1. So now I know I have carbon 2 through 5 that are chiral carbons. So it actually matters if it's on the left or the right, if it's on the top or the bottom, right? So there's an easy way to remember that. If it's on the left in a Fisher diagram, that means that it is going to go up on the ring. If it's on the right, it's going to go down. Okay, so go to carbon 2. Tell me about my hydroxide. My OH, does it go up or does it go down? It goes down. Now, I could draw my H going up, right? But this is technically a skeletal diagram. So do I draw my hydrogens? No, it just takes up lots of space. So we just kind of leave it off. So all you really have to do is draw your hydroxides. So tell me about carbon 3. Up or down? Carbon 3 goes up. Carbon 4 goes down. Carbon 5. That hydroxyl, the green one, is where? It's in the ring. So there's no up and down. And you've already dealt with this. Whoa, I just erased it. You've already dealt with this CH2OH. You put it here. So the only thing left would be a hydrogen. So you could put the hydrogen going down. But do we write hydrogens? No. Okay, so now, last thing that we have to worry about is our carbon 1. Our carbon 1 has what attached to it, in addition to being in the ring? It no longer has a double bond. It lost the double bond when it bound to the hydrogen. So now it has a hydroxyl and a hydrogen. Do we draw hydrogens? No. So there are two different ways that I could do this. I could draw, let me erase this, and I'm going to copy this. We're going to do it two different things. Copy, paste. Okay, we have two things that look exactly the same, right? I could draw my hydroxide going up, or I could draw my hydroxide going down, right? And the answer is either one is true. They both happen. But we have to be able to recognize them and write them differently. So when you're doing this, if you look at that carbon that is farthest away from the chiral carbon, and you look at the hydroxyl that's attached to that carbon that was in the carbonyl, if they're both going up, remember in a double bond, if we had both things going up, what did we call it? Cis, but we don't call it cis anymore, but we call it beta. So we call this beta. It's a B with a little long stick. But like B, C in the alphabet, right? B and C are close together, so they go together. In the other one where we put our hydroxyl down, our CH2OH is still up, so it's opposite. We call that trans, but we don't call it trans anymore. We call it alpha. We call it alpha. So now, do you have a carbon that's in a carbonyl anymore? No, there's no carbon-carbon, there's no carbon-oxygen double bond. So we can't say carbonyl carbon anymore. So now we call it, because it's in a ring, we call it the anomeric carbon. The anomeric carbon is the carbon that is bonded to two oxygens. It was the carbonyl carbon, and so it's very important to keep track of it. So if I went and I found my carbonyl carbon on the beta structure, it would be carbon number 1. Same thing in the alpha structure, it's carbon number 1. How do I know that it is the anomeric carbon? I look and it's bonded to one oxygen here, one oxygen here. Same thing down here, one oxygen here, one oxygen here. That's how you can look at a ring and be able to tell what was the carbonyl carbon and what is now the anomeric carbon. Okay, it is a big new vocabulary right now. So you need to practice those terms. I'm going to use them a lot, and the more you use them, the better off you're going to be. Okay, I think that was everything I wanted to cover on that. I left myself way more room than I needed, but that's okay. All right, so now that we know how we go from a straight chain into a ring, now we need to be able to analyze rings. you tell me, look at A, is this the alpha or the beta anomer? And then we'll explain why. Alpha or beta? This is beta. So this is beta, or you do, it's supposed to be either you write beta as a regular B or you do the symbol, either one. So how did y'all know that this was beta? We look at carbon that is farthest from the carbonyl carbon, right? We're always going to draw that as up. Now, where is my carbonyl carbon that is now my anomeric carbon? Bound to two oxygens, 1, 2, it's got to be right there. So I look at the hydroxide that's attached to it, and they're both what? They're both up. If they're both up, they are beta. So these are both up, and that's beta. Okay, look at A, alpha or beta? This is alpha. So if we look, we're going to look for our carbon that is farthest away. And then we look for our anomeric carbon. Here's one oxygen, here's one oxygen. That makes this the anomeric carbon. So the anomeric carbon's hydroxide is down. Carbon 6 is up. So we have one up, one down, one up, one down. We would call that trans, but we don't call that trans anymore. We call it alpha. Good? Practice, practice. Okay, now, this is where you have to draw from the Fisher diagram. So I could put you a question that says, okay, here's D, whatever, ultrose, whatever it is. Now, here are 4 answer choices. Which one is the correct ring structure? So are you going to have to hand draw it? No, but you might as well, and then just compare your answer to the multiple choice answers and find it, right? Okay, so we're going to make a bond. Go and find your hydroxyl that's on the chiral carbon farthest away from the anomeric carbon. That's over here, is going to bond with this carbon. So this is going to be 1, 2, 3, 4, 5, and the oxygen, which makes a 6-membered ring, and I have 6 carbons. So this oxygen right here is going to be this oxygen. I'm going to make my 6-membered ring. And I'm going to say this is carbon 1, 2, 3, 5, and then I'm going to go up with 6, CH2O H. Yeah. And I need to be a little bit over, because otherwise I'm not going to have room. Okay, so carbon 1, what are we going to do with carbon 1? That depends on if we're alpha or beta, right? So what do we want to be? Let's do alpha first. So if I'm alpha, what do I do with carbon 1? Carbon 1 is going to have a hydroxyl. It's going to be down. So OH goes down on carbon 1. That's my anomeric carbon right there. So carbon 2, does the hydroxyl go up or down? It goes up because it's on the left. Okay, carbon 3, does it go up or down? It goes down because it's on the right. It goes down because it's on the right. Carbon 4, whoa. Whoa. Our screen just went out on us. This is not good. It says PC. PC is currently selected. I swear I didn't touch anything. Okay, let's see. Let's see. It looks like touchpad has lost connection with the controller. Please reestablish connection. That'd be nice. That'd be nice. Oh, goodness. Nope. Are we back? No. Things just went green, but now they're back red, so I don't know. Video. I'm so terrified of pressing buttons. Uh-huh. We got one. We got two. I must have pressed the right buttons. Waiting for response to sync request. I don't know what that means. We're gonna keep rolling. If it's showing up, we're gonna keep rolling. Okay. I want it. Okay, I think we're back. All right. Now, what do we do? What carbon are we on? 4. Carbon 4, up or down? Carbon 4 is on the right, so we're going to go down. Okay, carbon 5 is already done. Be careful, it's already done. Already done, so you don't need to do anything with it. Yes. What do you, yes, it does. What do you mean?
Like the one you just wrote.
Carbon 4. This is carbon 4, this is carbon 5.
So why would it be HO if it's still H on there?
Oh, because I'm showing that the carbon is bonded to the oxygen. If you think that you can squeeze in the hydrogen here, you can. Just show that your carbon's bound to your oxygen. So it doesn't matter. That doesn't matter. I just didn't think I could fit it, right? So I put it here, but it doesn't make a difference.
So what I do is I extend the line and I put an H. Should I not be doing that?
So you're always going to make sure your line connects to your oxygen, because hydrogen can only make one bond and it's going to be bonded to the oxygen. So the oxygen makes 2 bonds, one to the hydrogen, one to the carbon.
So I would, like what I'm doing is drawing like a whole line to show like it's bonded to this and the hydrogen.
Oh, you don't. So if it's skeletal, you don't draw it. What she's talking about is she did this, right? Usually we mean in a skeletal diagram that that's a carbon.
Okay.
So unless you put a hydrogen here like that, that would indicate that you have a carbon there. So either you put the hydrogen or you don't put the other half of the line.
So it's okay if I do put the hydrogen?
If you do put the hydrogen,
Okay.
yes. But on the exam,
It's just gonna be like that.
well, it could be either way.
Okay.
Okay. All right. So now, yeah. Now we're going to take this and we're going to turn this, not cut. We're going to copy this and we're going to turn it into what? Beta. How do we turn this into beta? All I'm going to do is I'm going to erase my hydroxide and I'm now going to make it go up and I have beta. Super simple, right? Good. All right. Okay, now we need to talk about, where did I put that? Here. I put that in the wrong place. I want it here. Okay. So I want to show y'all something. This is from your textbook. This is simply from your textbook, and we talked about it already, but it's just a reminder. Okay. If I have 2 monosaccharides, right? Here are my 2 monosaccharides. I want to make a disaccharide. How do I make a disaccharide from 2 monosaccharides? I'm going to undergo what kind of a reaction? Be more specific. If I have 2 monosaccharides and I want to make a disaccharide, is it going to be hydrolysis or is it going to be condensation? Condensation, because in condensation, I take 2 molecules, I hook them together and I make a molecule of water, right? So that's exactly what happens. Do you see what's highlighted here? H and OH. What does that make? Water, right? So what I'm going to do is I'm going to take those red atoms away and make water. And then all I'm going to do is I'm going to connect this oxygen right here to this carbon. That's my new bond. And I'm going to make a disaccharide. So what does that look like? Scroll over. That's what it looks like. I took my OH and my H away, I made water, and I linked the two monosaccharides. So if I go in that direction, I have what kind of a reaction? A condensation. I'm going to make water and I'm going to join my two molecules. What happens if I go in reverse? I have a disaccharide. I add water to that disaccharide. It's going to break the water up, and you're going to give an OH to one and H to the other, and we call that hydrolysis or hydrolysis, right? And they're opposites of one another. Remember that? So this was just your reminder. If you want the figure, it's figure 6.10 in your textbook. Okay. All right. So now, oh no, it was out of order. It was in the right place, and I moved it to the wrong place. Anyway, we're going to use that in a minute. Sorry about that, y'all. We're going to use that in a minute. But first, we're going to draw some other molecules. I'm sorry, y'all. I got ahead of myself. Okay. So the other thing that we have to think about when we talk about reactions with sugars is monosaccharides and disaccharides, yes, but also oxidation and reduction. So do you remember your little trick to remember oxidation and reduction? Oil rig. So oxidation is loss of electrons, reduction is gain of electrons. What else are you gaining and losing? So if it's oxidation, you gain oxygen, you lose hydrogen. If it's reduction, you lose oxygen, gain hydrogen. So the electrons are really, when we talk about ionic things, we're really talking covalent now. So we're going to be talking about gaining and losing hydrogens. That's what we really, hydrogens and oxygens. So here's an example of diaerythrose. Diaerythrose is going to undergo a reduction. If I'm going to undergo a reduction, what are some things that could happen? I could either gain hydrogen or I could lose oxygen. So I'm going to tell you that this one is going to gain hydrogen. Where on this molecule can I gain hydrogens? Yeah, so remember when we did this and it was a carbon-carbon double bond, right? And we had H2. What did we do? We gave each of the carbons that was participating in the double bond, what? A hydrogen. So give each of the atoms that are participating in the double bond a hydrogen. So the carbon gets one and the oxygen gets one. So I'm going to say carbon, it had a hydrogen. I'm going to give it another hydrogen. Now, it's still going to be bonded to the oxygen, but it can't have a double bond because otherwise, how many bonds would it have? It would have 5, and that's no good. Right? So now I'm going to give, if I give this one a hydrogen, give this one a hydrogen, and get rid of this double bond, I end up with this. What's another way to draw that? It's exactly the same. I could say CH2OH and then do my 2 chiral carbons and then CH2OH. Remember we did that at the very beginning of class? Same thing. Both answers are correct. But you might see one in an answer choice. You know what I mean? Like, just make sure that you understand that those are the same thing. Yeah. Okay. All right. And then we did that. Okay. So now this is what I did. This is what I was doing, the monosaccharide and disaccharide. I'm sorry. I just got too excited about chemistry. You know, it happens. So 6.33 is identify the following reactions as condensation or hydrolysis. A disaccharide breaking into two monosaccharides. Do we have condensation or hydrolysis? Hydrolysis. A reaction in which two molecules combine, forming one, and a molecule of water is produced. Condensation. One thing I do want to say on your homework, do you see how this says a reaction in which two molecules combine, forming one, and a molecule of water is produced? Sometimes they're going to ask you to draw the product, but they'll say draw the main product. Is the main product of any condensation reaction water? No, so it's asking you to draw the sugar. It's not asking you to draw the sugar and water. So if you see that in a question, the main product is the one that has all the carbons in it, not the water, okay? All right, C, the breaking of a glycosidic bond. Hydrolysis. That's what we call the bond between the two monomers. We call that the glycosidic bond. Okay, now, the next thing we have to do is we have to be able to look at a disaccharide and name the bond. And I know that sounds very nitpicky, but it's not. Because you can have two of the same sugars that are linked together. And when you link them together in different ways with different glycosidic bonds, they have extremely different properties, extremely different. And we're actually going to talk about that later in this chapter. So for right now, what we want to do is we want to be able to identify what is the glycosidic bond. So when you're naming a glycosidic bond, you want the numbers of the carbons that participate. And you would do this like as in 1, 6, like it's the first carbon and then the 6th carbon. Here we are. Try to keep track of myself. Or we do the 1 carbon and the 2nd carbon, or you do the 4th carbon and the 2nd carbon, whatever it is, right? But this is the carbon from the first monosaccharide, and this is the carbon from the 2nd monosaccharide. Okay, now in front of that, you're going to, so that's part 1. Let me erase these examples. The other thing that you're going to want to do is you're going to want to name the orientation of the glycosidic bond for anomeric carbons. You only do it for anomeric carbons that are participating in the glycosidic bond. So sometimes you're going to have 1, sometimes you're going to have 2. So you might have a beta 1, 2. You might have an alpha beta 1, 2. So in the first one, there's only 1 anomeric carbon participating. In the second one, there are 2 anomeric carbons participating. Okay, it's different. And we're gonna see tons of examples. So let's try to do this one. So the first thing I like to do is I like to find my anomeric carbons. So in that first monomer, how do I find my anomeric carbon? I look for my carbon that's bound to 2 oxygens. So 1, 2 oxygens. This is my anomeric carbon. Is this carbon 1? Yes. If I had a CH2OH, would it be carbon 1? No, it would be carbon 2, but it's not. So we're going to erase that. Okay. So this is carbon 1, 2, 3, 4, 6. Okay. So now let's do the next one. Where's my anomeric carbon? I look for my 2 oxygens. My carbon is right there. Is that carbon 1? Yes. 1, 2, 4, 5, 6. So tell me the numbers of the carbon atoms that are participating in the glycosidic bonds. Do the yellow one first. So that's 1, and then we put an arrow to say, okay, it is 6 that is participating. So you put that into parentheses. Y'all with me so far? Yeah? Okay, now the next step is to look at the anomeric carbons that are participating in the glycosidic bond. How many anomeric carbons are participating in this glycosidic bond? Only 1, right? This one is anomeric. This one is anomeric, but it's not participating in the glycosidic bond, so we're not going to name it, right? So we look similar to as you did beta and alpha before. We look at the carbon that's farthest away. And now instead of looking for the hydroxyl, we look for the glycosidic bond. So are we going down or are we going up? Down. So we have an up and a down. What do we call this? Alpha. So this is an alpha 1,6 glycosidic bond. Yeah? Okay. All right. So for each of the following disaccharides, name the glycosidic bond and draw the monosaccharide produced by the hydrolysis. Okay, so let's name it first. Take a second, try to name it yourself, write it down. Any takers? You want to tell me what you get? What you get? Alpha beta 1, 2. That is correct. Okay, so let's go through and let's see how we did that. So on the top one, let's number it. Right? So here's my oxygen, here's my oxygen. This is my anomeric carbon. My anomeric carbon is 1, 2, 3, 4, 5, 6, right? Go to your second one. I have an oxygen here, an oxygen here. Here's my anomeric carbon. Is that anomeric carbon number 1? No, remember I've been warning you about this all class period long, right? This is carbon 1. My anomeric carbon is carbon number 2, 3, 4, 5, 6. So the carbons that are participating are carbon 1, and we start, it's like reading left to right and top to bottom. List the top one first or the one on the left first. So it's 1, 2, that's where we get our 1, 2. Then we're gonna look and we're gonna say, we have CH2OH, right? It's participating. I have a anomeric carbon that's participating. The CH2OH is going up, the glycosidic bond is going down. So that is alpha or beta. That's alpha, okay? Then what we're gonna do is we're gonna look at CH2OH and we're gonna look at that glycosidic bond. CH2OH is up, the glycosidic bond is up, so we call that beta. I did not mean to erase that, beta. So that's where we got all 3 of those things. Questions? Okay. All right, let's keep going. Oh, we got to make this into monomers, right? Okay, so we have our disaccharide. What did we say happens in order to make it into monosaccharides? You have to get rid of that glycosidic bond. Remember, one of the atoms, one of the molecules is going to get the oxygen. You give that one a hydrogen, and the other one you give a hydroxyl, right? Because we do this with what? Water. What kind of a reaction? Hydrolysis. Great, great, great. Hydrolysis. So the easy way to do this, I love this, is that I can just erase my oxygen, right? And then go in and add in hydroxyls. So this is my OH. This is my OH. The only thing you have to worry about is making sure that it's going in the same orientation. So if it was beta before, it should be beta after. If it was alpha before, it should be alpha after. Okay, does that make sense? Yeah. Okay, good. All right, let's try another one. Try to name this glycosidic bond. I'm going to copy it so that we can make monosaccharides in a minute. Okay, so name that bond. You're like, isn't that a game? We should have a game show. Name that bond. I don't think I'd have very many participants. It'd have to be really good prizes, right? So jot it down, whatever you think it is, write it down. Okay, any takers? Yes, sir. It is a beta 1,4. Whoa. It is a beta 1,4 glycosidic bond. Yes. Okay, so how do we do that? Find your anomeric carbons. So I find my anomeric carbons. Did y'all identify anomeric carbons? Yes. Okay, now number your carbons. So I don't have anything attached to the anomeric, so the anomeric is 1, 2, 3, 4, 5, 6, right? Do the same thing for the next one. I go 1, 2, 3, 4, 5, 6. So the two atoms that are participating are carbon 1 and carbon 4. So that's where I get my 1 and my 4. Now, where do I get my beta? I'm only looking at the conformation of the anomeric carbons that participate in the glycosidic bond. So how many anomeric carbons participate? Only the one in the first monomer. So I look, my CH2OH is up, my glycosidic bond is up and up is beta. Okay, now we have to turn this into 2 monosaccharides. So how do we do that? Hydrolysis or condensation? Hydrolysis, because we're going to add water and we're going to break up our molecule. So all you have to do is get rid of your oxygen, right? And then add hydroxyls. So let's do that. Remember, if it was up before, it goes up. If it was down before, it goes down. So in the first one, we were going up, that's OH, and here we're going down. Yes. If I told you condensation, you would have to take these 2 monomers and go to a glycosidic bond to make a disaccharide. That's correct. Because condensation is going from disaccharide to monosaccharides. Hydrolysis, I'm sorry, I did the other way. Hydrolysis is going from disaccharide to monos. Condensation is the reverse. Yep. Okay. Almost done. All right, so you remember how I said you kind of got to memorize some things? Yeah, these are some of those things, right? Okay, ordinary table sugar. If you're going to go and bake some cookies, I actually have some stuff to bake cookies. Charles has been begging me to make cookies, so we'll have to do that very soon. That fit the following descriptions. So what kind of sugar am I going to use in my cookies? Anybody? Sucrose? Sucrose is what you put in buy at the grocery store. Found in milk and milk products. We talked about this one. Lactose. Also called malt sugar. Maltose. Hydrolysis gives galactose and glucose. We talked about this. This was the question earlier today, but in the reverse order. This is lactose. Okay. See what we got next. All right, how much time we got? 44. So we ended here on 40, so I'm gonna call it and we're gonna end it here. So I think we're doing great on time. We'll have one more class of chapter 6, and that'll be awesome. If you have questions, please let me know. Make sure your exams go in the black metal tray when you are on your way out, if you haven't done so already. Have a happy Halloween. Eat lots of sucrose. Tag where we were. Right. So let me end. Did anybody have anything on the Zoom? Let me end the Zoom. Share. Okay.
Condensation, you go